In this example, similar to the monkeys climbing example, we have a constrained rope, and then we have a light rigid rod, and on that rod we have two particles connected with the mass of 1 kilograms and 2 kilograms. And while this system is at rest, there is a force in the horizontal direction by an amount of 60 newtons. And one thing to consider here is that on this rod, the location of these particles with respect to a frame that would be attached to the rod would not change, because we have this assumption of a rigid rod. So that's the information we have. There's our system. There's two external forces actually acting on the system. One of the external forces is this F force in the horizontal direction. The other is, if we consider the gravity in the downward direction, due to the gravitational loads of these two particles, there is a force in the downward direction. These are two external forces. And with respect to these external forces, there will be the acceleration of the mass center. So one part of the question asks us about the acceleration of the mass center, and that's something we need to calculate directly by using this F information, the force information, and the total mass of the system of particles, which is 3 kilograms. So it's quite straightforward for this part of the question, but then in the next part of the question, it asks us about the angular acceleration, theta double dot, of this rod or the system of particles that is connected to the rod, and they compose the system of particles. Now, for that, we can do a number of things. We can talk about the speed of these particles based on the assumption that as this F force will strike this, then as a result of that there will be the rotation. So due to this rotation, there will be the rotational speed of the system of particles and the rotational acceleration as another aspect of this. Now we can investigate these with respect to a specific location like this hinge point, or by using the relative angular momentum concept about the mass center. So we need to find out the mass center. Probably the mass center, you can guess the mass center at the moment actually. It will be closer to the 2 kilograms. How close it is? Well, you can do the math for that, but it will be 1/3 length here, and then 2/3 length will be here, and this is the location of your mass center. But you can choose a frame. You can choose to locate your frame at the bottom, or you can choose to locate the frame at the hinge point. Both would work to find out where the mass center is. And then you can make the respective calculation with respect to the selection of that frame actually. Well, in the solution of this question, the frame is selected at the bottom particle. So this is our frame to work with. Okay. And this was the first part where we calculate the acceleration, linear acceleration, and it's quite straightforward, and we talked about it. Now we need to find out the relative angular momentum's rate of change and make that equal to the summation of the moments about the mass center. Now if you take a look at this system again, there are two forces acting on the system. Like we said, one of them is the F force, the other one is the gravitational forces of these two. But we know that the mass center is lying on this rod around here, and as a result of that, this gravitational loads will not generate any moment about the mass center. So the only thing that we will consider there would be the F external force. So on the left-hand side of the equation, the only thing we're going to have is the F force times the location of the F force to the mass center. If you would define that as D, let's show that D distance here. The D distance will be the distance from this point to the mass center point. Oops, sorry about that. So this is our D distance from the F force to the mass center, and that would be the amount of moment about the mass center due to the external force. Now on the right hand side of the equation, we can start off by finding the angular momentum, not the rate of the angular momentum directly, but angular momentum. Now in order to find that, the first thing that we need to determine is the location of the mass center. Now we can already talk about it by inspection. It will be at 250 times 2 over 3, right, from the bottom frame, and you can also do this calculation in this way, as the location of these masses. This 0 is for the mass at the bottom, and 3 is the total mass. So this is total mass. Let's call it MT actually. And this is the mass with 2 kilograms. And as a result of that, we find out the mass center to be located exactly in the same spot that we had guessed. So exactly at this point. Then, in order to find the angular momentum, we are going to find it in terms of the relative angular momentum calculated about the mass center, because they're equal to each other. We will use the definition of the distance to the mass center, and then the relative, this is the relative velocity of the ith particle with respect to the mass center. Okay, so this rho I times theta dot is equal to that. Theta dot is the angular speed of this rod. This rod rotates with theta dot. And rho I is how far is the ith particle is from the mass center. Rho I is defined as the particle's location from the mass center. So in that sense, we can calculate the 2 kilograms location to be 0.25. This is 0.25 from the frame at the bottom, and then what we calculated as the mass center's location is 166 something, I guess, right? 166, yes. So the difference between these two is 250 minus 166 is its location away from the mass center. So this is its rho, if you call this particle 1 rho 1. And then rho is also used here, so that's why we have this squared term, rho 1 squared, and then this is rho 2, and rho 2 squared is appearing in the second part of this equation. And as a result of that, we get the angular momentum as a function of theta dot, the angular velocity. Now if you take the derivative of this term, then we get the time rate of change of the angular momentum, and the only parameter here as a function of time is theta double dot. Why? Because of our assumption here. The assumption is the rigid rod assumption. That means the location of these 2 kilograms with respect to 1 kilogram does not change within the frame defined on this system of particles, moving with the system of particles. So you can assume this as a rigid system in that sense. And as a result of that, the only variable here is the angular speed, and then by taking the derivative with respect to time, that's the only part that we need to use for finding this derivation. So we get a term in terms of theta double dot, and that is equal to uh, the force times the distance of this force from the mass center. So this is that distance. This is the distance that we have defined as the d distance before, and 60 is the force, external force acting on the system. On the right hand side of the equation, the unknown is theta double dot, so we end up with finding the angular acceleration to be 336 radians per second squared.